Hi, I'm Gary Rubenstein, and in this video I'm going to show you a derivation of how an Indian mathematician named Madhava might have created a sine table back in the late 1300s. So we don't have writing specifically from Madhava, but we do have this table that you see, and what that table is values for the sine of 24 angles, basically starting at 3.75 degrees. So in increments of 3.75 degrees, which is 1/24 of 90. So there's 24 angles going from 0 to 90 degrees in increments of 3.75 degrees each. And even though we don't have writings by Madhava, we have later Indian mathematicians doing commentary about the table, and this mathematician, Jayastava, wrote this book, which I will not try to pronounce, around 1530, in which he explains the formula that Madhava likely used, and he gives a derivation of it. And these are the formulas that he says Madhava would have used. And if those formulas, if you're a mathematician or if you took calculus, those formulas might seem familiar to you. You might say, those aren't Madhava formulas. Those are the Taylor series expansions for sine and cosine. Well, Taylor was hundreds of years later. So if Madhava used these formulas, he anticipated them, Taylor, by hundreds of years. In this book, in this 1530 commentary, they definitely have these formulas. So what you're going to see in this video is not me showing you Madhava's writing, because we don't have his writing, and it's actually not going to be me showing you this Jayastava's writing, because it's really difficult to understand that way. But in one of my favorite books by Canadian mathematician Glenn Van Brummelen, he wrote a book called The Mathematics Behind the Heavens of the Earth. It came out in 2009, and it's the early history of trigonometry. He actually wrote a sequel of it also. And he explains his sort of explanation of the mathematician from the 1530s. But what you will see is my interpretation of what Van Brummelen did. I try to simplify his argument a bit, make it a little bit easier to understand. So you're seeing this filtered through a lot of different people, me being the last of them. So in these derivations, at some point, we're going to need these sums of powers, which were known at the time. So these are the sums of the sum of consecutive odd numbers, or sum of the squares of consecutive odd numbers, or cubes, or fourth powers. And at least this very first one was known for a really long time. In 500 BC, the ancient Greeks knew this as part of their number theory, that if you can see here a little pattern, that if you add up the first, if you add up the consecutive odd numbers starting at 1, you get 1 for the first one, 1 plus 3 is 4 for the second, 1 plus 3 plus 5 is 9. And it seems that you're always getting a perfect square, the square of the number of terms. And that is true. And in ancient Greece, they could have used this like a geometrical explanation that I really like a lot. One of my favorite proofs without words. You can see the red circle represents the number 1. Then there's an L shape, upside down L, with 3 orange circles representing the second odd number. And then each sort of new L shape is the next odd number. And when you add it, you'll continually get a square. So when you make it instead the sums of the squares or the cubes or the fourth powers of the consecutive odd numbers, there's a bit of a pattern. You can see the numerator goes up, doubles each time, whereas the denominator increases by 1 each time, and the exponent on the end increases by 1 each time. So these formulas are going to come in handy later I only kind of informally proved the first one, but I'm telling you that these other formulas are accurate.
Now, to understand what this proof is about and to appreciate how difficult of a thing that they were doing is, let's just make sure I can explain what's meant by finding the sine of an angle. So here I have a quarter circle, and I have this angle here, which can change. It could be a small angle, could be up to a 90-degree angle. Now, something related to the sine is the arc length. So here we have, in this 60-degree angle, across from it you have what's called a 60-degree arc. Now, the length of the arc is something that's actually fairly easy to calculate, and that's because it's known for thousands of years that the uh, circumference of a complete circle with radius 1 is equal to 2 pi, which is about 6.28. So when you have an arc, let's say you have an arc that is from a 60-degree angle, that's going to be 1/6 of the full circle. 1/6 of approximately 6.28 is 1.05. But arcs are a lot easier than what are called sines. I'll get into what those are in a second. When you see that if you take this arc, the 60-degree arc, and if you change the angle to 30 degrees, so the arc was 1.05, and when I pull this thing down to 30 degrees, now the arc is about 0.52, because the arc is exactly, of the 30-degree angle, is exactly half of the arc of the 60-degree angle. The 60-degree angle is 1/6 of the full circle. The 30-degree angle, the arc for that, is 1/12 of the circle, so it's half. So in that way, they're kind of like proportional. As the angle grows, if the angle's twice as big, the arc's twice as big. If the angle's 3 times as big, the arc is 3 times as big. Now, the arc's going to be important in this derivation I'm going to show you. But here's what's meant by the sine. If I make my angle, let's say I make my angle 20 degrees, what is meant by the sine is the length of this line segment. That line segment that's kind of perpendicular to the horizontal, this vertical line segment, that's what's meant by sine of 20. And you can see there's some relationship between that red line segment and the green arc. Well, all we could really say is that the red line segment is shorter than the green arc. You could imagine it's sort of a straight line. If you dropped something straight down from that where the radius hits the circle, it would go in a straight line down towards the horizontal. Whereas the curved line kind of does not take the shortest path to get down. So one thing we can see, just for starters, is that the sine is always smaller than the arc. And one idea, you might say, well, maybe there's some sort of relationship between those. Like when it's a 50-degree angle, the sine is 0.77 and the arc is 0.87. Well, how are those related? Well, it turns out that it's about 14% larger. The arc is about 14% larger than that vertical line segment. And you think, well, maybe that's always true. That would be great. That would help us. But it turns out when I change the angle down to, let's say, 35 degrees, well, the arc is smaller and the sine is also smaller. But the ratio between them, now it's only 7% bigger. So unfortunately, that how much the percent changes, and it seems that the smaller the angle gets, the closer they both shrink when the angle gets small. But notice how when it's 18 degrees, the arc is only 2% bigger than the sine. And as I get closer and closer, they actually get, it says 1, but they're never exactly equal, but they get really close. So we're not going to be able to just find a relationship between the arc, which is easy to calculate, and the sine, which is hard to calculate. Now another line segment that's significant in this picture is this line segment that I just made blue. We'll call that the cosine of 40. And just as the sine changes when the angle changes, the cosine changes, but notice when the angle's small, the cosine can get pretty close to 1, or actually can get equal to 1 if the angle actually becomes 0. And the bigger the angle gets, the smaller the cosine gets. So those are the sort of players at action here. There are 3 of them, actually. There's the arc, there's the sine and the cosine, and they're going to be related to each other, but in a pretty complicated way that we're going to explore through the Madhava calculations. Seeing the value in a chart might give some insight into what's going on here and what the issues are. Here's a 10-degree angle, and over here in the chart, 10-degree angle, that arc length is about 0.175. That's this little arc length here. And the sine, this vertical line segment, is pretty close to it. It's a little smaller. It's 0.174. And this dot here, this point, that's also, the line segment from this blue point to this black one shows what the sine of 10 degrees is. Now, when I double it, we see here this 20-degree angle, and we see sine of 20 represented by this line segment here, or this point here. And here on the chart, you can see that the arc has doubled, but the sine has not doubled. It's a little bit less than double. And I have this column here for delta sine. How much did sine change by? It changed by 0.168. It's almost double, but it's a little bit less than doubling. And here I'm just going to keep going. 30, 40, 50, 60, 70. Oops, too far. No, there's 70. So let's take a look. First of all, the arc is doubling and tripling and quadrupling and so on. You see delta arc, that's always the same. The arc is proportional to the angle. But the sine, first it goes up by 0.168, then by 0.158, then by 0.143, then by 0.123. So the change in the sine is shrinking. It's getting smaller as the angle gets bigger. Sort of to go from sine 10 to sine 20, it goes up by about 0.168. But from sine 20 to sine 30, it only goes up by 0.158. And that difference is shrinking. And that's why it's such a hard problem, because we're trying to get a formula for sine, but the amount it changes by is changing itself, but it's changing in such a way that is sort of, as the angle gets bigger, the difference between the sine of that angle and an angle that's like 10 degrees more is smaller. So that's just something to think about for a minute. Now this picture has even more going on. I've got the 70-degree angle, which makes this line segment here, sine of 70, and I also split it up into 7. These points here are every 10 degrees, so we split the 70-degree angle, or the arc, into 7 equal pieces of 10 degrees each. And in this chart here, we have the sine and the cosine of each of these angles, and the sine's getting bigger while the cosine is getting smaller. And here we have how the sine is changing, how much it's going up by, and the sine's going up by a smaller amount each time, whereas the cosine, which is getting smaller, is changing in sort of the opposite way, or it's changing by more of an amount. So it goes up by 0.04, and then 0.07, and then 0.1. So they're sort of changing in different ways. As the angle's getting bigger, the sine is changing at a smaller amount, and as cosine's getting bigger, the cosine is getting changed by a bigger amount. Now they have a couple more columns here. You notice how the change in the arc, that's always the same. Now, if you divide the change in sine divided by the change of arc, look at what happens. It becomes about 0.9798 for the first change and 0.9052 for the second. And it's very close to what the cosine value was. See, it's only off by a little bit. It's changing as it gets bigger, but it's pretty close. And the same thing happens with if you take the change in cosine and divide it by the arc length, it's very close to what the sine was. And it gets even closer if I increase how much I'm breaking the angle into. So here I'm breaking it into 16 pieces. And now you can see that the difference between change of cosine divided by arc and the sine is actually smaller than it was before. And if I make it really so many, if I divide the angle here up into 59 pieces, it's practically the same. This is going to get us a relationship that's really important. Here's another nice illustration. I have a 30-degree angle here, and the green is sine 30, and the yellow is cosine 30. And then I have this small additional angle of 5 degrees, which makes this red vertical line segment sine of 35. And the difference between them, if I just remove this piece, is just this little red thing. And you can see here that that little red thing has this length of 0.074. But if I were to divide that by arc AB is this little tiny blue arc, it's 0.843, which is very close to cosine 30. And if I change the angle, the bigger angle that is, and just make it go up by 5 degrees, you can see that how much sine is changing by is proportional to the cosine. And the closer to 0 that changes, the angle, 0 is too small, but if it's like 1 degree, you can see these numbers here are very close together. As I move this, you can see how the change in sine is proportional to the length of the cosine. And this little red line segment is the change in the cosine. As you can see, it's 0.064. And if we divide that by the arc length, that little blue arc length, we see that the change in cosine is actually proportional to the sine. Here my increment is just 5 degrees, and you can see those numbers are pretty close together, namely this number and that one. And if my change gets even smaller, let's say it's just a 1 degree change, these numbers are even closer together. So what I'm getting at is that the change in cosine is proportional to whatever the sine is, and the change in sine is somehow proportional to whatever the cosine is. And this is all going to be worked into this derivation. In order to follow this derivation, there's some notation I'm going to introduce, and this isn't like standard math notation, but it's going to be really useful for understanding the derivation. So first of all, here I have a picture, and my angle here, I'm going to call that theta. And if that's the case, if that theta happens to be 70 degrees in this picture, this red line, as discussed before, is sine theta. And this arc here, I'm going to call that S theta, arc length. I'll put parentheses around this also. So now this angle is cut up in this case into 1, 2, 3, 4, 5, 6, 7 pieces that they're all 10 degrees long. So each of these arcs individually are actually equal to each other. And all of them could be called S of theta over n. So for this picture, just theta is 70 in this picture, and n is 7. But the theta could be different size, and the n could be bigger or smaller. Another observation, each of these things could be called S of theta over n. And individually, they also happen to be, they could be written as S theta, the original S theta over n, that way. Now, here's the small theta over n angle right here. And that makes this red line segment sine of theta over n. And here's another theta over n angle. Together it's 2 theta over n, so this line segment here could be called sine of 2 theta over n, and this is sine of 3 theta over n, 4 theta over n, and so on. So a shorthand notation for sine theta over n is going to be sine with a little subscript of 1. So if theta and n were different, sine 1 would be a different thing, but in this case, so basically sine 1 is shorthand for sine theta over n, and sine of 2 theta over n is going to be called sine with subscript 2. So that's talking about the lengths of these line segments. Now these line segments have different lengths, and as the angle gets bigger, the sine gets bigger also, but not in the same way the arc does. See, when you double the angle from theta over n to 2 theta over n, the arc here doubles. It's exactly double. But the sine doesn't double. The sine changes by different amounts. I'll use a different color here. I'll use like a green. So from sine 1 to sine 2, this line segment is kind of like the difference. I'm going to make this little right triangle here to make it easier to see. See these triangles here? In these triangles, you can see that, make it yellow, these lengths here are how the things change. And that amount is different for each one. There's even a starting one from there. So here comes a new notation for us. I'll say the difference between sine 1 and sine 0, we're going to call that delta sine 1. And the difference between sine 2 and sine 1 we'll call delta sine 2, and this pattern will continue for this notation. So this yellow line, this first one, is delta sine 1, and that's delta sine 2, and that's delta sine 3, because it's how much bigger sine 3 is than sine 2. Now, there are similar notations for cosine. See, the cosine values are these horizontal lines. So this would be cosine of 0 degrees, and this line from here to here would be cosine of 10 degrees, and this line would be cosine of 20 and 30 and so on. As you can see, those lines are getting smaller. So here comes some notation for you. This this second green line, this one, that's basically cosine
of 10, but we'll call that cosine 1, which is shorthand for cosine theta over n. Whereas this shorter line, this next one, that's basically, we'll call that cosine 2, because it's cosine of 2 theta over n. And if I wrote it in here, this is cosine 0, cosine 1, cosine 2, cosine 3. And the cosine values are getting smaller, and how much they change by, for instance, this little piece here, that's the difference from cosine 1 to cosine 0. Cosine 0 minus cosine 1, we'll call that delta cosine 1, and cosine 1 minus cosine 2, we'll call delta cosine 2, and so on. So in this derivation, you're going to see a lot of things like sine 1 and cosine 1, or sine 2 and cosine 2, and you'll see these delta sine 1s and delta sine 2s and things like that. So you'll be familiar with what those different things mean. And in this picture, I have the orange lines are all the delta sine 1, delta sine 2s, and so on. And the blue lines are all the delta cosine 1s and delta cosine 2s. So there's a relationship between this red line, which is sine theta, is also the sum of all these orange lines together. Well, those lines, so I could say sine theta, each of those little ones is a delta sine something. On the other hand, if this green line here is cosine theta, and these little blue ones are delta cosine 1, delta cosine 2, and so on, the relationship is that the cosine theta, it's not quite the sum of those things like it was with sine, but it's 1 would be the entire radius minus the sum of all these little blue things, which are delta cosine 1 plus delta cosine 2 plus delta cosine 3 plus dot 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 plus delta cosine n. So these are some of the relationships and notation that are going to be used in this derivation.
This diagram is going to get used to prove an important relationship. I have here a 70-degree angle, and I can cut it up into equal numbers of pieces. Let's just cut it up into 7 pieces. They're all 10 degrees now. And one of these angles, one of these little 10-degree angles, I can bisect. For instance, here's the first one, but I could also move. So I have kind of an angle bisector here. I can move it to a different spot. Now, on this angle bisector, I'm going to make a I'm going to make a triangle. And just here I have these 2 triangles, blue triangle and a red triangle. Now I'll explain what all these things are, but for now let's just take a look at how those 2 triangles change when I change sort of which angle I bisect. The thing to notice is that the red and blue triangle are going to turn out to be similar to each other, and that's going to be really important.
So before we saw that sine, the change in sine was somehow proportional to cosine, and the change in cosine was somehow proportional to sine. And this is the key element in the relationship that gets used in this derivation. And in modern calculus, this is something that you prove with derivatives. But there's a nice sort of geometrical, sort of informal geometrical proof of this that I'm going to show you, and I'm going to use this diagram. Here I have a 70-degree angle. They'll call that theta. And it's cut, in this case, into 5 pieces that are each 14 degrees. Now, this line segment here we call sine subscript 1, and this line segment here we call sine subscript 2. That's 2 of the theta over n's. And this one here is sine 3, and this one here would be sine 4. So if I bisect this angle right here, this point right here would be at the, let's see, it's 14, 28, 42, 49 degrees would be the point there. So this line segment here, which is one side of this blue triangle, in terms of this n and theta, we could call it sine 3.5. Oops, subscript 3.5. And that's one side of this blue triangle. This blue triangle also has a hypotenuse of length 1. And this side down here, it would be cosine of 49 degrees, which we could write as cosine subscript 3.5. It's 3.5 of those theta over n's, which individually reach 14 degrees, which is 70 divided by 5. So that blue triangle has sides 1, cosine 3.5 of those theta over n's, and sine 3.5. It's a right triangle. Now this little red triangle, it has as its sides this length right here is the difference between this is sine 1, 2, 3, between sine 4 and sine 3. So we can call that delta sine 4. This would be delta sine 1. This line here would be delta sine 2. This would be delta sine 3, and that's delta sine 4. And likewise, down here, that's the difference between cosine 3 and cosine 4. So we can call that delta cosine 4. Now there's still hypotenuse of this red triangle. And that line segment, the thing about that line segment is that it's very close to the length of this arc, especially the higher the value of n is. But even for a fairly small value of n, this red line segment is extremely close to this red arc. So it's approximately s of theta over n, the arc length, which is also equal to s of theta over n this way, and we can even write it as delta s. That's just a shorthand for that. Now, that's not really the hypotenuse of that triangle, but it is close enough to it, and especially when n is a large number, it gets even better. Now, the red triangle and the blue triangle actually turn out to be similar. let's just see. In this case, this angle is a 49-degree angle. I'll just call that alpha. So that would make this angle up here 51 degrees, which is 90 minus alpha because of this right angle. Now in the red triangle, we have a right angle. And here we have the 51-degree angle up here, which makes this angle, I'll make it red, this angle over here would be 49 degrees, which would be alpha again. But then we have this, I'll make it like a green right triangle. That has a right angle in it also. This this chord, this is like it's like a big isosceles triangle, this one here. So that angle bisects, there's also altitude, which makes this red angle here 90 minus alpha, 51 degrees. But then if I go back to the big triangle, not the big one, but the red one, that would put an alpha right here. So the blue and the red triangle are actually similar to each other. And when triangles are similar, we can set up a proportion. For instance, if I use the side opposite the 49-degree angle, I could say sine 3.5 over 1, which is the hypotenuse, is delta cosine 4 over delta s. And if I sort of cross multiply, I get delta cosine 4 equals sine 3.5 delta s. Or, so that's going to be an important relationship. If instead I use the side opposite the 51-degree angle, in the blue triangle, it would be cosine 3.5 over the hypotenuse, which is 1. And then in the red triangle, I'll use the side opposite the 51-degree angle, which is delta sine 4, and the hypotenuse is, maybe we should call this approximately, because that delta s isn't officially the hypotenuse because it's an arc, but it's going to be really close, especially when n is a large number. When I cross multiply, I get delta sine 4 equals cosine 3.5 delta s. And these can be generalized further by saying delta cosine n is equal to, approximately equal to, sine of n minus 1/2 delta s. And for the other one, delta sine n is equal to, or approximately equal to, depending on how you feel about that arc, cosine n minus 1/2 times delta s. These two relationships are basically what we do, like, it's pretty advanced formula about the relationship between how cosine changes and what sine is. Pretty much equivalent to the modern way of saying that the derivative of cosine is sine and the derivative of sine is cosine. But this is proved with a really nice sort of informal geometric picture.
And before we get the big proof started, a quick reminder that for very small angles, the sine of the angle, which is that red vertical segment, is very close to the green arc, which is the arc of the angle. So here, for 11 degrees, at least rounded to the nearest hundredth, they're equal to each other. And the smaller the angle gets, the closer those two things get together. Even when the angle is sort of big, 23 degrees, they're still really close together. But for small angles, they are practically equal. And the closer the angle gets to 0 degrees, the more equal those two things are. So that's going to be used when you see sine theta is approximately arc theta. That's what we're talking about.
So using these relationships, we can get
a formula for an approximation of cosine theta. And the insight is that cosine theta, which is this red line here, can be thought of as the difference between this green line, which is 1, minus all these little blue small segments. But those blue segments are also over here, and we have a shorthand for that. We call those delta cosine 1 plus delta cosine 2 plus up to delta cosine n. Now we have a formula here, the second one. With that, we can replace these delta cosine n's with sine 1/2 delta s plus sine 3/2 delta s plus all the way up to sine, we'll call it 2n minus 1 over 2 delta s. And now I can factor out the delta s. And inside the parentheses, I'll just have the sine 1/2 plus sine of 3/2 plus up to sine of 2n minus 1 over 2. Now this sine 1/2 is actually itself shorthand for sine of theta over 2n. Sine 1 is sine of theta over n, so sine 1/2 is theta over 2n plus sine 3 theta over 2n plus sine of 2n minus 1 theta over 2n. Now, all of these sine expressions using this first formula can be replaced with s of theta over 2n plus s of 3 theta over 2n plus s, that's the arc length, and now I can do a little bit of manipulating this stuff. For instance, I can factor out from each of these expressions an s theta over n. I could even put the over n here. And I end up with just 1 plus 3 plus 5 up to 2n minus 1. And we have a formula from before. Here, I'm going to bring this s theta over n fully out. And this 1 plus 3 plus 5, that equals n squared. Now, this delta s is actually shorthand for s of theta over n, or s of theta and then divided by n. So I'm going to write 1 minus s of theta over n. Oh, I lost my 2 somewhere. There it is. Sorry about that. All of these had a 2 in the denominator. So I get 1, here's the 2 there. I end up with this, s theta over n times s theta over 2n times n squared. Well, the n squareds cancel out with these 2 n's, and we end up with our new formula, which I'm going to put up here, because I have room for it now, or that's the only place I have room for it. Cosine theta is approximately 1 minus s theta. I'm going to put brackets so I can square that over 2. And that formula is going to be the starting point, or something we're going to use in the next iteration. Now we can get a better approximation for sine theta in a similar way. We say, well, sine theta which I'll make as this red line, is also the sum of all of these line segments, this one, and that one, and that one. They were orange, but I'm tracing them over in yellow now. Well, those things can be thought of as delta sine 1 plus delta sine 2 all the way up to delta sine n. Now, this is going to get a little bit more tedious. Using formula number 2, I can replace all of these delta signs with, in this case, cosine 1/2 delta s plus cosine 3/2 delta s all the way up to cosine 2n minus 1 over 2 delta s. Now using formula number 1, actually, before I do that, let me just remind you that cosine 1/2 is actually shorthand for cosine theta over 2n. And cosine 3/2 is really a shorthand for this. Now, we can do a couple of things here. We can factor out the delta s. I lost my delta s here and here. We factor out the delta s, and we replace each of these cosine things with what we have here, our newly generated formula number 1. So we get, oh, and I see here, that's not the whole thing over 2. Sorry about that. It's just that piece over 2. So we get 1 minus s of theta over 2n. I hope you don't mind. I'm not going to put brackets. I'm just going to put a square here and just say that it's the whole arc squared, s of theta over 2n squared over 2, plus 1 minus s of 3 theta over 2n squared over 2, all the way up to the last one, which is 1 minus s. We have to say 2n minus 1 theta squared over 2. Okay, it's looking pretty ugly, but it's going to simplify pretty nicely. You'll see why. So first of all, notice there's a lot of 1s, 1 plus 1 plus 1. There's n of them, so that's just going to add up to n. Now this other stuff, I'm going to write it like this, minus, because they all have minus in them. And if you square, if you actually go ahead and square this thing, in fact, I'm going to, 1 minus parentheses s, it becomes theta over 2n. Actually, I think I'll make it, I'll skip a step here. This thing can be turned into s of theta squared over 8n squared. You see, you can pull out the denominator, the 2n, and then when you square it, it becomes 4n squared, and then together with this 2 becomes 8n squared. So the next term, it would turn into actually 3 squared s of theta squared over 8n squared. And that's going to go up to 2n minus 1 squared s of theta squared over 8n squared. So now I can factor out from each of those things the s of theta squared over 8n squared. And what's left inside here is 1 squared plus 2 squared plus 3 squared up to 2n minus 1 squared. I'm going to change this delta s back into this one. And then I'm going to actually distribute it to the two terms. So in this first one, it just becomes s theta because the n's cancel out. This becomes s of theta cubed over 8n cubed. And inside these parentheses, there's a formula that the sum of the squares of the consecutive odd numbers is actually 4n cubed over 3. And when you put this together, you get s of theta minus this n cubed cancels out with that one, and this 4 cancels out with the 8, and you get s cubed minus s theta. This time I will put the brackets back in. Cubed over 6. And we can add that in as a new formula that's going to give us approximations for sine theta. S theta minus, oops, that looks like squared, but that's just part of the denominator there. S theta cubed over 6. That 6 is also equal to 3 factorial if you're trying to make it look more modern. For the next step, we start the same way we did before, with saying that cosine theta is going to be 1 minus the sum of all these little blue lines. That's delta cosine 1 plus delta cosine 2. And then we can use formula 2 here to replace those delta cosine n's with sine with fractions times delta s's. So it's going to get pretty hairy with all this stuff, but let's see what happens. So these sine 1/2 delta s's, just like before, I'm going to factor out the delta s's from all those. And the sine 1/2 is actually a shorthand for sine of theta over 2n plus sine of theta 3 theta over 2n all the way up to sine of 2n minus 1 theta over 2n. Now, each of these things, 2 steps ago, we replaced them all with s of theta over whatever the angle was. But now, instead, we're going to replace it with this thing. And yes, it's going to get a little bit complicated. But let's see what happens. So this sine theta over 2m, that turns into s of theta of 2n minus s of theta over 2n cubed. That cubed, I'm not going to put the brackets from here, but know that it means that, over 6, that's this 6 here, plus s of 3 theta over 2n minus s of 3 theta over 2n cubed over 6. I'm just going to say dot, dot, dot. Now, there are these positive terms, and then there's the ones that have minus in front of them. So let's just group them separately. So for all the ones that are positive, I can factor out an s of theta over 2n. And then we end up with just one of them here. But this, because I could basically bring this 3 out here, when you're dealing with the arcs, you're allowed to do that. So it becomes 1 plus, oh, but that 3, yeah, 1 plus 3. And it's going to end up being all these odd numbers. Now, inside the parentheses here, I also have the minus. I'll factor that out, the minus sign, because these all are negative. And this gets more complicated. It's S is going to be S of theta cubed is what they all have. Plus this 2 gets cubed, and the n gets cubed, and the 6 is down here. So we end up with 2 cubed is 8 times 6 is 48 n cubed. And inside the parentheses, here there was a 1, here there was a 3, but it got cubed. So we end up with 1 cubed plus 3 cubed, all the way up to 2n minus 1 cubed. Okay, it's going to start getting cleaner now. Good news. We got past the hardest part. 1 minus, good idea to change this delta s back into s theta over n, which I could even put the n under here. And I distribute that through, and it becomes s theta squared. This n goes here, and the 2n can go here. And this 1 plus 3 plus 5 we saw before can turn into n squared. Now this delta s gets distributed through, so it goes here, but it also goes with this. That can become a plus at this point because I'm going to get rid of the parentheses. So plus, we end up with s theta to the 4th power over 48, and this n cubed turns into n to the 4th. And the sum of all the cubes actually can be replaced with 2n to the 4th. And we put this all together, we end up with cosine theta equals 1 minus s theta, I will put the brackets back in, over 2. We already had that one from before, but now we have this extra term. The 2 cancels out with the 48, and the n to the 4ths cancel out, and we get s theta to the 4th over 24. If you like, you can call that 24 4 factorial if you want to make it look more like the modern thing. So I'm going to do one more iteration just for a good measure. Just like 2 steps ago, I could say that sine theta is the sum of all the changes in the signs. And I could replace all those delta signs with cosines times delta s. I can factor out the delta s. And all these cosine 1/2, just as a reminder, those are actually shorthand for this. This is equivalent to what we did before 2 steps ago. But now I'm going to replace each of these cosines with the new formula, which has 3 terms in them. So it's going to get kind of ugly, but let's just see. Try to explain it carefully. So this cosine theta over 2n can be replaced with 1 minus s theta over 2n squared. I'm just going to put the square there, over 2, plus s theta over 2m to the 4th over 24. That's just the first one. the second one turns into a similar thing, but there's going to be a 3, so 2n squared over 2 plus s of 3 theta over 2n to the 4th over 24. I'm just going to say plus dot dot dot. So let's see what happens. First of all these ones, there's just 2 of them there, but there's a total of n of them. And these middle terms, which I'm going to factor out a negative. If I actually work this thing out, it would become, after pulling out the factors and things from it, it would become s theta squared over 8n over 8n squared. And this one here would be like almost the same expression. So this one is just one of them. Or sorry, I'll call it 1, but I'm going to call it 1 squared. Whereas this one is similar, except this 3 would get squared, so it would become plus 3 squared. I actually have enough room now to throw this guy back in. And finally, these guys, the ones with the pluses, those would turn into, I could factor out an s of theta to the 4th power. Let's just look at this first one. Over, this 2 gets to the 4th power also, so 16 n to the 4th, and then times 24. I'm actually going to write 16 times 24 n to the 4th. And inside the parentheses is going to be 1 to the 4th. This 3 here is going to turn into 3 to the 4th. And I'm going to have the sum of the 4th powers of the consecutive odds. Okay, that's the hardest part, because now I can distribute this delta s, which was always s of theta over n. When I multiply that through, the n's cancel out, and I just get s of theta. When I multiply it by this one, I end up with s theta cubed over 8n cubed. And this whole thing gets replaced with 4n cubed over 3. And when I send this s theta over n distributed to this thing, I get s theta to the 5th power over 16 times 24 n to the 5th. And the sum of the 4th powers, I said before, was 16 n to the 5th over 5. Now, the n cubes cancel out, and the 4 cancels out with the 8, so that gets us what we had before. This 3 gets together with that too, so I get s theta, I'll put that in brackets, cubed over 6. Now over here, this n to the 5th cancels out with that n to the 5th, and this 16 cancels out with that 16, and I'm left with s theta to the 5th. 24 times 5 is 120. If you like to make it look more like the modern expansion, you can do it like that. So what we've gotten are these two formulas, and it seems like if you kept doing this, which I'm not going to, but if you did, it seems like the pattern would continue with just the next odd number, and so on. And for these ones, it would just be the next even number, and so on. And that concludes this video about the Madhava formulas. This derivation is not, I'm not claiming that it's a very rigorous proof, but it definitely gets to a correct result. And it's really interesting that it came up so many hundreds of years before the Taylor came around and rediscovered it. So I hope you like that. Um, hope you like that proof. It was hard to learn. It was hard to make this video, but I hope you like the way it came out.